I was working in the shop the other day with a machinist, and we're working on a setup on the grinder actually. And I mentioned to him, well, you just need to trig out this little length of this triangle or something like that. And he kind of indicated that him and math or whatever didn't get along too good together, and he didn't really know how to do it. And this kind of surprised me because he's been a machinist for quite a while, and it got me to thinking, what would be the minimum required mathematical ability, mostly with trigonometry, you would need to know, or you would use on a daily basis, I guess, to be a machinist? Because you don't have to know a lot, but you do need to know a few things. And I thought I'd make a little video about this subject. Now, they make these calculator things, and I have one of these, like this Machinist Cal Pro, and to tell you the truth, I've never used this thing, or I've only used it a few times. I got it because it's kind of like interesting, but I think it's, you got to do all of these various key pushes and everything it shows here, and to me it's kind of like more complicated than using a regular calculator actually. I don't know if I've ever really used it, maybe a few times. This is the calculator that I use. It's a Texas Instruments TI-30X. I looked it up on Amazon. You can buy this thing for like $9.50 off of Amazon. And I pretty much just buy one and put one at every machine so I don't have to look for it and carry it around, because they're so cheap. You can, get them for next to nothing. And this actually will do everything you really need to know how to do, or you will need to know being a machinist. And it's pretty simple to use. I like this particular one. This is maybe just my preference really, but I like this because of the simplicity of the way the keys, you push them, and the second keys and stuff, and the way it, a lot of calculators you have to calculate the sine, cosine, tangent, and various things like that first, and then do it. This one you kind of do it after. I'll kind of demonstrate that in the middle of your calculation. It's a little bit easier for me to use anyway. I don't know. It's just my preference, and I've gotten used to it. All these calculators do the same thing, really. You could even use the one on your cell phone here. The calculator here, the regular calculator is like that, but if you turn this thing sideways, you get a full mathematical calculator, just like this thing does. And it does the same things, except, like I say, I don't like the way this thing works as much as this one. Although it will do the job, but so on this subject, what do you really need to know? What's the minimum you need to know, or really mostly what you use in doing machine work? And there's a couple of things I think that you kind of really essentially need to know. One has to do with a circle, and you need to know how to calculate the circumference of a circle, which is the diameter times pi equals the circumference of a circle. And then you need to know how to calculate the area of a circle, which is the radius squared times pi equals the area. That will pretty much get you by with everything you need to know about a circle for the most part. You would need to know the area times the length, and multiply that times the weight of whatever material you're working with to calculate the weight of a round bar. Obviously, the weight of a square bar is just the length times the width times the height of the bar. Same thing, but you need to calculate the volume, and so to calculate the volume of a round bar, you need to know the area of the bar, end of the bar, times the length. And I only remember these two numbers right off the top of my head. Is aluminum weighs 0.1 pounds per cubic inch. I'm dealing with inches here. You'd have to convert your various things to metric dimensions. I mostly deal with inches, so that's what I remember. And steel is 0.2833 pounds per cubic inch on steel. And as to a circle, that's pretty much most everything you need to know. You know, you could get by not knowing anything else about a circle except that. I mean, there's other things, but these are the main things that you're going to use every day practically as a machinist. You need to know the circumference. Well, what do you need to know the circumference for? I should say that. If you're going to calculate surface footage of a tool, which is kind of important, you might want to know, well, how much speed or RPM I want to turn my tool at a various material. Like if you had a 1/2-inch end mill, you could do it this way. There's straight calculations for this. I'm not going to really go into that, but if you don't remember those, you can just say 0.5 times pi here equals 1.570796. So if I stored that in the memory of this calculator, and I could take 12 divided by that circumference of the tool equals 7.639 turns to make that 1/2-inch end mill has to rotate 7.639 times to go 1 foot on the length. So it's surface footage. If you know that number, then I can just store that here again and say I want to go 200 surface footage times that many times to revolve for 1 foot, and it would equal 1,527 RPM. So that's kind of what you need to know how to calculate circumference for mostly. You probably won't use it for a lot of other things. I mean, if you were doing sheet metal work and you need to know what the length of to wrap a piece of sheet metal around a circular object of some sort, well, you'd do the same thing. You'd calculate the circumference and then you would cut the metal based on that. But in machine work, mostly this is kind of the thing you're going to do as far as knowing the circumference of something. There is a precision like flexible scales where you can wrap it around the part and measure the diameter, and you can actually measure it pretty precisely because it increases your accuracy, if you will, or your resolution, I should say, by the amount of pi when you wrap a scale around a circular object. And so, you know, if you're going to measure plus or minus 5/1000ths of an inch, well, that's 15 thousandths on one side of the dimension and 15 on the other, so it's 30 thousandths, which is a 32nd of an inch. You can pretty much see that pretty good on a scale if you just wrap the scale around the part. You know, if you got large diameters and you don't have mics for those, you can actually get within plus or minus 5 pretty easy if you have one of these flexible scales. They make them to do this exact thing. I've never used one, but they might even have divisions on them that measure diameters and everything. I don't know, somebody in the comments would probably be able to tell us that. But so that's kind of, for a circle, you kind of should know that stuff. Now for everything else, practically everything else, you can use a triangle to calculate things. So if you have a right triangle and one corner is 90 degrees, there's various calculations for a right triangle, and they're pretty easy to remember. And these calculators, you know, you can fill in the blanks and everything and it gives you the number, but if you just don't have that calculator, you can do the calculations very easy with the length times the sine of this angle equals the length of this side. So if I was to demonstrate this, let's just say 0.845, let's call the length of that side 0.845 and this point, I don't know, 325, okay, like that. Well, if I want to know the angle here, like, see, say I just knew the lengths of those two sides and I didn't know the angles. Well, now I could calculate them if I know the lengths of these two sides or the length of any two of the sides. On a right triangle, all of the angles added together add up to 180 degrees. So if this is 90 degrees, which every right triangle has a 90-degree angle in this corner, then these two angles have to add up to 90 degrees to make 180, and whatever angle this is, you can subtract this from 90 and get this other angle. So you only need to know one angle of the right triangle. So on this calculator, kind of the reason I like this calculator, let me see if I can demonstrate this and you can see it if I don't get too much reflection on things. If I take this number, let me see here, okay, maybe you can see that. If I take this number, 0.325, divided by 0.845, and I go equals, okay, that's 0.384615, and if I push these buttons in this sequence on this calculator, you know, I can give you probably the technical names for all these, but really, if you just go second tangent, which is the other tangent, the reverse of the tangent, if you will, and then second answer equals, and it gives me that angle of 21.0375 degrees, which is the angle here. I'm going to store that in the second memory of this calculator. So 21.037. I'm going to just round that off because I'm going to use this stored memory to prove that this answer is right. Okay, so if I take 0.845 times the tangent of that angle, I'm going to recall the angle here from the memory, equals 0.325. See, so I like the way this calculator works because you can just push a sequence of keys and get the answer pretty easy. So these calculations, the tangent of this angle times this length equals the length of this side. Or if you don't know that, you know the lengths of the sides. This side divided by this equals what I'll call the inverse of the tangent, and gives you that angle on this calculator. The second of the tangent, on the second, they call it tangent dash 1, you know, cosine dash 1, sine dash 1 on this calculator. So if I wanted to know the length of the what they call the longer side of the triangle, the hypotenuse, I would take this number divided by that angle would give me the length of that side. So if I take 0.845 divided by the cosine of, I'll recall that memory again, equals that. So this is 0.9, I'll write this on here, 0.9053 for the length of that side. I'm going to store that in the next memory of the calculator. You have like 5 memories in this simple calculator, but it's enough to do what you need to do. So if I wanted to verify that that was right, the sine of this angle times that number, that length of that side equals the length of that side. So 0.9, here I'll just recall it, memory times the sine and I'll recall the angle I stored there, equals that, and you can see, I don't know if you can see those, 0.325. So with this little simple $9.50 calculator, you can pretty much do all these calculations. You don't need any tables, you don't need anything, you just push the keys in the right sequences for the most part once you kind of memorize those, and you can just get this stuff just that easy. You know, you could do the same thing with this, but you almost have to do it more key pushes with this thing than this, in my opinion anyway, once you get used to this very simple calculator here. So these are the various calculations of a right triangle. I mean, I could go into all these, but you kind of need to know these calculations to solve for a right triangle. You can kind of almost build any shape with a combination of circles and triangles, mostly triangles, to lay out what you need to do as machine work. You know, whether you're programming and you need a radius and you need to know an I and a J value from the start to the center of that radius. You can build those values calculating with these triangles or various things like that. So this to me is the bare minimum of the math you need to know to be a sort of a competent machinist. You need to know these two equations on a circle. That's about really all you need. You know, if you want to calculate the weight, you got to multiply it by the length and the weight of this. I guess you call it the specific gravity. This is in cubic inches, but you know, you could convert that to metric dimensions if you are dealing with, you know, millimeters and, you know, centimeters and whatever, you know, meters. But I'm working in inches, so I'm giving the examples in inches here. But the same thing works in metric sizes too. Exact same equations. There's of course there's the obviously, you know, a squared plus b squared equals c squared. I never use that calculation because it's just as easy to do it this way for me. It gets more confusing when you got to take the square root of the side and all. I don't even go there with that usually to do those kind of calculations. Just the tangent of this angle times the length equals the length of that side. Tangent of this angle times this length equals the length of this side. The sine of this angle times the length of this side equals that side. So this kind of comes into play when you're dealing with sine bars, because the long side of the triangle is the sine, and that's why they call it a sine bar. Then you have these two rollers on your sine bar, and if you know the length, most sine bars are like 5 inches long. So you say the 5 inches times the sine of whatever angle you want to set will tell you how many gauge blocks, you know, what size gauge block stack you need to put under this side of the sine bar. You know, if this is your sine bar, like that, to get the angle you need. So that's another, just a right triangle calculation. The sine of that angle times the length of that side. And the neat thing I like about this calculator is all you got to do is type in the length of your side. You go like this is 0.9, whatever it was. I stored it in the memory, times the sine, and you just go the sine, you know, 30 degrees, and you would need 452 thousandths of gauge blocks to make this a 30-degree angle on that. So that's, I don't know, you know, maybe this is kind of, I don't know if you people are interested in this kind of a video showing this stuff, but to me that's the bare minimum mathematical calculations that you kind of need to know. And you could just memorize these are pretty easy. You just memorize these equations going the direction you want, and you know, dividing it is the opposite of multiplying it. So when you divide this by this, and you take on this calculator the second value of tangent, and it equals, and it'll give you that angle to do that, you know. And if you don't know this angle but you calculated one of them, you subtract that from 90 degrees, you get that angle, and you can do the same thing going this direction with the triangle calculations. So to me, that's really all you need to know. You know, we could look at a practical example. I kind of drew this on CAD, and I kind of tried to make it so we can see it decently. And say you had to measure here, and you had to get half of 500 thousandths, we'll call it, half-inch diameter. This will be an 82-degree countersink in a part, and you need to set the depth of your tool or something, so you stand off of it and run it, and you measure the diameter of this. But if you want to measure it accurately, or if you have to hold it very close for some reason, you can take a sphere, a ball bearing, whatever you have. I drew this with a 0.3125 diameter sphere or circle, if you will, in this countersink. And you know what you would want to know is the height here to put your micrometer, you know, one of those mics on the part here, and measure the height of the ball as it sits in the countersink, and that would tell you you're at the diameter. This is, you would do that. You do this kind of thing quite often. So the easy way to figure that out is you have a triangle here. I drew it in red. I don't know if you can see that on the video, but the triangle looks like this. I'll draw it out here. it looks more or less like this. That's one triangle, and the other triangle is this right here, which is your whole half of your countersink. And so you just need to calculate these two triangles. So here's the countersink, half of the countersink, which is 0.25 here, and this angle on an 82 degree countersink will be 41 degrees, or half of 82, and this will be 49 degrees. 41 from 90, because this is a right triangle and this is 90, so they all add up to 180, right? So 41 from 90 is 49, so we need to know the length of that side right here, obviously, which would be, I'll do it right here, the 0.25 times the tangent of 49 equals, I'm going to store that in the memory so we don't really have any rounding errors, but it's 0.2875, okay? There. And we would need to know the length of this side of this triangle that comes up to the center of our circle or sphere ball that we're putting in there, which is this side here, and we know this is half of 312, which would be 0.3125 divided by 2. There again, all these example is in inches, okay? So it's that 0.15625 is 0.15625, not that side, this side. This is the 90 degree angle right here between the ball and the countersink. And so we would need to know the length of this side. Well, if this is 41 degrees again, this has to be 49, right? So in order to get the length of the long side of the triangle, we would have to divide by the cosine of this angle to get the length. Let me do it here, divided by the cosine of 49 degrees equals this. So that's 0.2381, which I'm going to store in the third memory of this thing. So now we just have to subtract. If we know the length of this side, which is the total depth to the theoretical sharp point of our countersink or chamfer tool or whatever, then, and we subtract the length of that, we get to the center of the sphere, right? And then all we have to do is subtract that to get the height, or we got to subtract the whatever's left from the radius of the sphere to get the height here. It's that simple. So let's see, I think I stored all those in that's this minus that equals that minus our 0.15625 minus the answer that we just got equals that. So this length over here is 0.1068. Well, we'll just round it. Well, that'd be, 107 thousandths if you're miking it. So that's just sort of a example that you quite often do in machining, is you do that example I've just demonstrated, because you're measuring your countersink. It's kind of hard to measure the diameter with the calipers or scales or something. They do make special micrometers, but not everybody has those things. I don't have one that measure, because you have to have one for each specific angle of countersink. So you got to have one for every different type angles you do, and it's kind of almost, well, some of them the anvils hit on the corners here. I guess if you trust that, and your angle of your micrometer is less than your countersink, or whatever, so it doesn't hit the down in the countersink, that will work. But I don't really have any of those, and they're kind of a little bit expensive. Probably cost a couple $100 a piece, and you got to have a separate one for all the angles if you really want to do it correctly. Because if you do use one that just hits on the corner here, it would probably be close enough for most everything. If you deburred anything at all, it would be inaccurate, like for final inspection, it couldn't be used because a part would be deburred. Also, sometimes you have a much closer tolerance on these with steeper angles, some kind of seat or something for a valve or something. So this is the better way to do it. And I've even used drawings that specify to measure the chamfers or countersinks or seats, valve seats, this way by specifying the ball size and the dimension to some place to do it on the part, like from, if it's down in a hole from the top down to the ball or whatever. So I'm just giving that simple demonstration, but you can carry this out as far as you want to do, bolt hole patterns around a circle, and you just, if you have the holes and you just lay out the triangles to the center, you can calculate all of these things because you know the radius of your bolt circle and the angles you're dealing with. You'd have to figure out the start angle of the first hole and whatever, but you can calculate every one of those and just step it off on a digital readout and drill the holes. Nowadays with modern CAD softwares, I guess this is almost becoming obsolete, but what you really kind of should know this if you're going to be a machinist, because someday you're not, you don't have certain things to use the CAD software and you got to calculate it, or if you want to just do a quick calculation, which was the case when we were setting up something on the grinder, and the guy looked at me kind of like, well, I don't know how to do that calculation. And it kind of surprised me because this guy's been a machinist for like 30-40 years, and yet he doesn't have the confidence in being able to do this to do it. So you can get along, I guess, somehow with not knowing this as a machinist for many years, but you really should try to learn it if you want to be a machinist and do your job. So anyway, I don't know, is this kind of video, let me know in the comments, if this kind of video is at all useful or interesting. I could do a video on also what I think the minimum requirement for measuring tools, to get started as like maybe a young machinist trainee or a apprentice or something like that, because you really should, some shops don't let you use your own measuring tools because they have to calibrate them, so they don't even let you use them. And other shops, people, they don't have what they want and they're borrowing from other people, and I kind of resist loaning my tools out to other people because they can come back damaged or out of calibration for some reason because they did something to the tool and I might not realize it. And so I kind of resist doing that, and I think a lot of more experienced machinists don't like to do that either. So there is sort of a minimum amount of tools you kind of need to have, or you should make an effort to get if you're going to be serious about this profession to do it, But anyway, let me know in the comments if this kind of video is of any interest at all to you. We kind of take this stuff for granted, people that have been doing this a long time, and we don't think about these kind of things, but there might be people just getting started that are thinking, well, what do I really need to know? And believe me, if you knew how to do all the calculations associated with a right triangle to get the lengths and angles of all the sides and everything, and you knew these two simple calculations for a circle, you could pretty much get by your whole machinist career with just knowing that, because there's a lot of people that don't actually know that much, believe it or not, that have been working as machinists for many years. So anyway, let me know in the comments. So thanks for watching.